Hey everyone, and welcome. Today, we're going to peek under the hood at one of the most critical but maybe least appreciated parts of our digital world, memory. Seriously, it's this invisible engine that's powering literally everything, from the phone in your hand to the biggest data centers on the planet. And as we're about to see, its limits are actually shaping the entire future of technology.
So, for years, we've all been obsessed with one thing: processor speed. Megahertz, gigahertz, right? But what if I told you that's not really the bottleneck anymore? What if the biggest thing slowing down AI, big data, even your brand new video game, is a traffic jam happening somewhere completely different? Okay, so let's get right into it. This huge problem, this central challenge in all of modern computing, actually has a name. It's called the memory wall. And you can think of it as this fundamental traffic jam that's happening deep inside every single device you own. So here's the key thing to get your head around. Doing the actual math, the computation, that's super fast. It's actually really energy efficient. The real problem, the thing that costs us so much time and eats up so much power, is just moving the data from where it's stored to the processor that needs it. And for something huge like an AI model, this isn't just a small delay, it's a full-blown crisis. Think of it just like this. On one side, you've got your processor, which is just lightning fast, ready to go. And on the other side, you have the active moving data, which is slow, it's an energy hog, and that is what creates this memory wall. This right here, this is the battleground where the future of computing is being fought. So, how do we fight back against this slowdown? Well, our first line of defense is a special kind of memory that works right alongside the processor. It's called DRAM, which stands for Dynamic Random Access Memory. This is the fast stuff. It's the computer's short-term working memory. But, and this is a huge but, DRAM has a catch, a really big one. To get that incredible speed, it's designed in a way that makes it, well, fundamentally unstable. The best way to think about it is that every single bit of data is stored in a tiny microscopic bucket of water that has a hole in it. So here's how that works. Each little bit, a 1 or a 0, is stored as a tiny electrical charge in a capacitor. But that charge, it leaks away almost instantly. So to keep your data from literally just evaporating into thin air, the system has to frantically run around and refresh every single bit. It does this by reading the data and then writing it right back where it was, over and over and over again. And when I say frantic, I am not kidding. Every single one of the billions of memory cells on a single chip has to be refreshed every 64 milliseconds. That is insane. Before you can even blink your eye, your computer has already checked and rewritten its entire working memory multiple times just to keep it from disappearing. Okay, so how in the world do you pack billions of these leaky buckets onto one little chip? Well, you can't really build outwards. There's no room, so you have to build upwards. Engineers have basically become microscopic architects, building these tiny 3D skyscrapers for every single capacitor. The scale here is it's mind-blowing. The aspect ratio of these little structures, that's their height compared to their width, can get close to 100 to 1. To put that in perspective, that's like building a tower that's 100 stories tall on a foundation that's only 1 story wide. It is an absolutely incredible feat of precision engineering. Okay, so DRAM is great for the work we're doing right now. But what about the data we need to keep when we turn the power off? That's where a totally different kind of memory comes in: flash memory. This is the stuff that's in your solid-state drives, your USB sticks. It's all about long-term, stable storage. The magic trick behind flash is something called the floating gate. You can basically think of it as a tiny, perfectly insulated prison for electrons. By forcing electrons into this little prison, you store a 0. If you pull them out, you store a 1. And because it's so well insulated, those electrons stay trapped for years, even with no power at all. It's brilliant. And, the invention of flash back in the 80s just completely changed the game. It took us from these big, bulky, mechanical things like magnetic tape and spinning hard drives to the tiny, silent, and incredibly fast solid-state drives that we all use today. It was a true revolution in storage. But it turns out not all flash is created equal. There are 2 main types. NOR flash connects its cells in parallel, kind of like lanes on a highway. This makes it really fast to grab any one piece of data, which is great for storing code that a computer needs to run. NAND flash, on the other hand, connects its cells in a series, more like a long line of cars.
It's a bit slower for finding one specific thing, but, and this is the key, you can pack way, way more cells into the same amount of space. And that incredible density is exactly why NAND is what you'll find in pretty much all mass storage today.
All right, so we've got our fast, leaky DRAM for doing work and our dense, stable flash for storing things. But we still have that annoying memory wall, right? To really, truly solve that problem, we need to completely rethink what memory even is. So, welcome to the future, the world of computing in memory.
This is one of those beautifully simple, elegant questions that's driving this entire field. If shuttling data back and forth is the biggest bottleneck we have, what if we could just stop? What if the memory could just do the math right where the data is already sitting? So look at the difference. The old way is this inefficient four-step dance. Fetch, send, compute, send back. The new way, it's just one step. The calculation happens inside the memory itself. The memory wall doesn't just get smaller, it gets demolished.
And this is where it gets really wild, so stick with me. In this new model, you don't store an AI's brain as just ones and zeros. You actually store its knowledge as the physical properties of the memory cells themselves, like their electrical resistance. Then, you feed your inputs as voltages, and the literal laws of physics, in this case Kirchhoff's law, perform a massive parallel calculation instantly. The memory stops being a passive warehouse for data and becomes an active factory that actually computes. It's incredible.
So the big takeaway here is this. The next great revolution in computing, that next huge leap forward for AI, it might not come from building an even faster processor. It might come from creating memory that can actually think. And when our data can compute all by itself, what new worlds will we be able to build? Thanks for joining me.